Okay, we're going to change gears here and investigate electromagnetic waves and light. And one of the great contributors to this theory, and one of the great scientists of all time, theoretical scientists, is James Clerk Maxwell. Here's James Clerk. Lived from 1831 to 1879, so I guess he died at the age of 48. I don't know what it was about the scientists in the 1800s, but they seem to die much earlier. Usually physicists live to grand old age for some reason. Was important for developing the kinetic theory of gases, explained the nature of Saturn's rings, also explained color vision, interpreted electromagnetic fields, and which is what we're discussing here, which resulted in Maxwell's equations, which coincidentally has the same name as Maxwell himself. What are the odds? And developed the electromagnetic theory of light. Here are some of Maxwell's assumptions. We have two charges, and electric field lines will originate on positive charges and terminate on negative charges. These are assumptions that we associate with electric fields, and is something that we've talked about in physics too. Magnetic field lines always form closed loops. They do not begin or end anywhere. So there's no such thing as magnetic monopoles. They can't start or stop anywhere. They just form continuous closed loops. Even if you look at something like a permanent magnet right here with the north and south pole, the magnetic field lines go all the way through, so they form a continuous closed loop through that. Even if you cut the magnet in half, still forms a closed loop. Assumption number 3, magnetic fields are generated by moving charges or currents. Here I have a solenoid configuration with electric charges moving around in the loops, generating these magnetic fields that go through the solenoid and on the perimeter. And a varying magnetic field will induce a EMF voltage and hence an electric field by Faraday's law. So here we have a magnet going into a coil, and that's generating electricity, which can be shown as this voltage on this meter. Maxwell predicted that electric and magnetic fields play symmetric roles in nature. He concluded that visible light and all other electromagnetic waves consist of fluctuating electric and magnetic fields, each inducing the other. This is part of the brilliance of Maxwell, and why we regard him so highly, is to realize that changing electric fields were generating the magnetic fields, changing magnetic fields were generating the electric fields, and the waves themselves were alternating this automatically. Brilliant. And then Einstein would go one step further and at some point show that if you change your reference frame, you can actually make all the fields electric or all the fields magnetic, depending on the reference frame and how fast it was moving. So that's even testament to how brilliant Einstein was. Here's an example of this brilliance. Consider a capacitor with current flow. We have a circuit that's running. It's got a capacitor. A current is running in, charging these plates, and we have a current running out. So we have a functioning circuit here with a capacitor in the middle. If we were to choose a loop around the first wire, we could apply Ampere's law to the path, and we know that the dot product of the B field along this path, along this circle, B dot ds, should be proportional by mu naught to the current enclosed by that circle, and the current being I going through the wire. Sounds good. That's a perfect application of Ampere's law. But what would happen if we tried to apply Ampere's law to the middle of the capacitor? So we have a gap here, and we have a closed loop there, and we're going to apply the magnetic field over that loop. However, we're not enclosing any wire. So there are no electric charges, no electric electrons moving through that closed path. And somehow we still have a current on the other side. So this is a contradiction. We would say B dot ds is equal to no current enclosed 0, but that can't be, because we can't have a current coming in here and all of a sudden have a current going out with nothing happening in between. So Maxwell defined a displacement current, I sub d, that was equal to epsilon naught, the derivative with respect to time of the electric flux that flowed between this gap. Hence, we know that the electric flux should be the integral of the E field dotted with the area through this gap. And we know from previous chapters, chapter 24, that the E field is equal to the surface charge density sigma divided by epsilon naught. 1 over epsilon naught times the charge per area. And if we dot that with the area, then we're going to get rid of the area, and simply the flux will be equal to the charge divided by epsilon naught. Put this into the displacement current definition, and we have that I sub d is equal to epsilon naught, derivative of the electric flux with respect to time. So that's going to be epsilon naught times 1 over epsilon naught, which will cancel out, times the derivative of the charge with respect to time, but that simply is equal to the current. So we have this displacement current is actually equal to the current, and that allows us to have continuity through the gap of this capacitor. How about that? Brilliant. These kind of ideas lead to Maxwell's wonderful equations that describe all electromagnetic phenomena. We have Gauss's law, which is that the integral of the E field over some surface area is equal to the charge enclosed by that surface area over a constant epsilon naught. We also have Gauss's law in magnetism, that the magnetic field over a closed surface is equal to 0, because there's no way you can enclose a magnetic monopole. You always have these closed loops. We have Faraday's law, says that the E field over some path is equal to the negative change of magnetic flux that goes through that path with respect to time. And we have the Ampere-Maxwell law, which we were just talking about, that the B field over some closed path is proportional to the current, and if there is no electric current, then it's the proportional to the change of electric flux through with respect to time through that path. And sometimes we add a fifth equation for Maxwell's equations, and that involves the force on a charge in an electromagnetic field. So you have QE for the electric field, QV cross B for the magnetic field. That's called the Lorentz force. And all these equations, these 5 equations, help describe all electromagnetic phenomena as one of the greatest achievements in theoretical science of all time. Here is it, the same 5 equations in even more beautiful form. If you define the operations of the curl and the divergence in mathematics, then you have these 5 equations in very simple form. It's so beautiful to see that all electromagnetic phenomena of nature that we know is described mathematically in such simple terms. It is really something that can make you appreciate the nature of it. So these equations, these Maxwell's wonderful equations, describe all electromagnetic phenomena in a vacuum. Later, Heinrich Hertz would write, "One cannot escape the feeling that these mathematical formulas have an independent existence and an intelligence all their own, that they are wiser than we are, even wiser than their discoverers, that we get more out of them than we put into them. I love this statement, and the middle part where it says even wiser, or wiser even than their discoverers, kind of puts a thought in about scientists. When they discover something, a lot of times they kind of give themselves the credit, for that phenomena, even though that phenomena exists, whether they discover it or not. Like if Newton discovers gravity and describes gravity, well, gravity doesn't suddenly appear because Newton discovered it. It was always there. The beauty was always there. Newton just described it. And so really the discoverers kind of, take credit for it, and they kind of feel smart about it, but it was always there even before they discovered it. It would still be there even if it was never discovered. So it's kind of a funny idea about how scientists feel about things. Here's Hertz's confirmation of Maxwell's predictions. Heinrich Hertz, 1857 to 1894, lived to be 37. So again, a lot of these brilliant guys in the 1800s, they kind of burned out, or something happened in the 1800s that they didn't live to be old scientists like scientists normally do. First to generate and detect electromagnetic waves in the lab, he showed that radio waves could be reflected, refracted, and diffracted just like light. In essence, he was showing that radio waves were the same nature as light, and that electromagnetic waves and light were the same thing. In the process, he really invented radio waves before Marconi, and should get credit for that, but doesn't get credit for that. He invented the radio waves and then started working on them, and then went beyond the communication by Marconi. The unit Hertz is named for him. Another coincidence, just happens to have the same name as he does. He's a scientific predecessor to Tesla. They kind of worked on similar ideas of working with electromagnetic stuff. In fact, Tesla is very famous for what's called the Tesla coil, which can generate very large electric fields and break down the air in the vicinity, and you can see these discharges in the air. So that we attribute to Tesla. Hertz had something very similar. He has what is called the Hertz donut. Have you ever heard of the Hertz donut? Well, if you haven't, let me try to explain what the Hertz donut is. Here's Heinrich Hertz and James Clerk Maxwell, and they're having a conversation. And Hertz says, "Hey, Maxwell, want a Hertz donut?" Oops. "Why, yes, I believe I certainly would." "Hertz donut." "Why, yes, I believe that certainly does." Okay. I have to credit Jerry Smith for giving me the puppets. Jerry Smith, probably future senator of Alabama, former Phi Theta Kappa president for the region here, gave me these. These are actually this is actually Tesla and Einstein, but they don't really make them for Hertz and Maxwell. So, thanks. Here's Hertz's basic LC circuit. We have an inductor, a capacitor, a switch. When the switch is closed, there is a continuous transfer of energy between the capacitor, which is storing electrical energy, and the inductor, which stores magnetic energy. The circuit will resonate at a particular resonant frequency equal to 1 over the square root of the inductance times the capacitance. We had a similar idea in AC circuits. Here's an experimental setup. He's got a transmitter and a receiver. transmitter of this device here, and a receiver which consists of just one wire with two little spheres. Has its own inductance and capacitance and natural frequency associated with it. When the transmitter is set to the natural frequency of the receiver, then we find that energy is transmitted, presumably through empty airwaves. So there is no electrical connection between these two devices. Energy was being transmitted through the air, and we could see a spark run when the frequency was just right at the resonant frequency. Hertz's conclusions: he hypothesized that this energy transfer was being taken place by a form of waves, now known to be electromagnetic waves. He confirmed Maxwell's theory, showing that these waves existed and they had all the properties of lights. They traveled through empty space. They had different frequencies and wavelengths. We talked about them being refracted and diffracted. He also confirmed Maxwell's theoretical speed for these electromagnetic waves as being speed equal to wavelength times frequency equal to 3 times 10 to the 8 meters per second. How about that? How beautiful is that? So experimentally, he showed that these electromagnetic waves have the same speed as light. Essentially, his setup is an antenna type setup where you have an alternating voltage moving electric charges within a conductor, and the movement, if you keep on adding energy, the energy has to go somewhere, and so that energy goes into the form of an electromagnetic wave. So it's radiating that energy as the charges are moving along the conductor. It forms electric field lines along that conductor, and we have an electric field wave emanating from that point. Also, as this current is moving within the conductor, there is a magnetic field that is varying perpendicular to the direction of the current. So the oscillating current will generate this oscillating magnetic field, and that will spread out from the antenna perpendicular to the direction of the electric field. So you will have these electric field and magnetic field magnitudes heading out in the form of an electromagnetic wave, and as a wave, it is transferring information and energy like all waves do. Example would be if you were sitting in a pond. I don't know why you'd be sitting in a pond, but if you were sitting in a pond and you're just kind of sitting there and all of a sudden a wave came along, and you would recognize by the action of the wave that, hey, you know what? Something over there fell in the water. And hence, in a sense, that wave transmitted information to you. It told you that something had fallen in the water. And if the waves were large, you would say, well, something large over there fell in the water. So it's transmitting information and energy to you in the form of a wave. Not so specific in terms of water wave, but light waves can be much more informational. So summary, charges and fields. Stationary charges produce only electric fields. Charges in uniform motion at constant velocity produce electric and magnetic fields. Charges that are accelerated, so that you're putting energy into this system, produce electric and magnetic fields and electromagnetic waves. These electromagnetic waves are indeed transverse waves, with the electric field and the magnetic field perpendicular to each other and perpendicular to their direction of motion. We'll show this a little bit later. But in this case, we have electric field, magnetic field, 90 degrees to each other and perpendicular to their direction of motion indicated in this diagram. Consider this. This electromagnetic wave is moving along, and the electric field vector is going to pass through a certain area. And if we were to evaluate Faraday's law over this square, then we would evaluate the electric field over the perimeter of the square. And on the right-hand side here, the electric field will be actually in the same direction as our ds. On the top, it's going to be perpendicular 9 degrees. On the other side, it's going to be 180 degrees opposite the direction of ds, like that. And then on the bottom, it's going to be at a 90-degree angle. So we're going to evaluate Faraday's law, E dot ds, around this square, and for that matter, we're going to evaluate the change in flux through that square as well, magnetic flux. If we look at the left-hand side of this equation, and we look at the left-hand or the right-hand side of this square, we're going to have E plus dE times L, which will be E dot ds for that part. On the top, we're going to have a cosine of 90 degrees, which will give us 0 for the dot product. On the other side, we're going to have a cosine of 180 degrees, because they're in opposite directions. That'll give us a negative 1, so we'll have a negative E times L. And on the bottom, we're going to have 90 degrees, again, cosine of 90, which will give us 0. Adding all these terms together, we'll get that the integral of E dot ds is approximately equal to L, the partial derivative of the E field with respect to x, dx. Looking at the right-hand side, the change in magnetic flux with respect to time, the flux is going to be the field times the area, and the area in this case is going to be equal to L times dx. So we have that the right-hand side of the Faraday's law is going to be negative L dx, partial derivative of the magnetic field with respect to time. Equating the two in Faraday's law, getting rid of an L and a dx on both sides, we have simply that the partial derivative of the E field with respect to x is equal to the negative partial derivative of the magnetic field with respect to time. How cool is that? If we evaluate a similar thing over the xz plane and evaluate the Ampere-Maxwell law over that plane using the same kind of integration as what we just did for the Faraday's law, we would get a similar type result, that the partial derivative of the magnetic field over the dx is equal to a negative mu naught epsilon naught partial derivative of the electric field over time. Taking the x derivative of the previous equation, we get the partial derivative with respect to x, the second partial derivative of x with the E field is a partial derivative with respect to x of the partial derivative of the magnetic field with respect to time. Bear with us, we're going somewhere with this. Rearrange that. Substitute in for a partial derivative of the magnetic field with respect to x from this second equation. And we have that the partial derivative, second partial derivative with respect to x of the E field is equal to mu naught epsilon naught, second partial derivative with respect to time of the E field. Beautiful. A wave equation. We actually will end up with two wave equations. This one that we just saw and a similar one for the magnetic field. The partial derivative, the second partial derivative of the magnetic field with respect to x is equal to mu naught epsilon naught, second partial derivative with respect to time of the same field. Note that if we describe the E field and the magnetic field as wave functions with maximum amplitude cosine angular wave number k x minus angular frequency omega t, do that for the magnetic field as well. Substitute these into these wave equations. We would get from the first one the second derivative with respect to x of this wave function, mu naught epsilon naught second derivative with respect to time of the same wave function, and conduct those derivatives. We're going to get out on the left, we're going to get a negative kx, or k squared, wave function, mu naught epsilon naught negative omega squared, same wave function, get rid of the wave function and the negatives. And we have now that omega squared over k squared is equal to 1 over mu naught epsilon naught. Omega angular frequency, k angular wave number. And we know from our wave treatment in physics 2 that the speed of the wave, the velocity of the wave, is the angular frequency over the angular wave number. We'll designate that as C. C is equal to omega divided by K. In this case, that's going to be 1 over the square root of mu naught times epsilon naught. We have used C for the velocity here. What's the value of this? Well, mu naught is 4 pi times 10 minus 7. Epsilon naught is 8.85 times 10 minus 12 in the SI system. Take the square root of that, 1 over that, and you get 3 times 10 to the 8 meters per second. Wow. So theoretically, based on these wave functions, you come up with a speed of these electromagnetic waves, theoretically, of 3 times 10 to the 8 meters per second. This is precisely the velocity of light, so this implies correctly that electromagnetic waves are the same as light, or vice versa. Light is an electromagnetic wave. Maxwell found this theoretically, just as Heinrich Hertz had found this experimentally. Note also, if we have the partial derivative of the electric field with respect to x is equal to a negative partial derivative of the magnetic field with respect to time, putting in our wave functions, evaluating our partial derivatives, we have a negative k E max sine kx minus omega t equals a negative omega B max sine kx minus omega t. Get rid of the sine functions. And with a little bit of rearranging, we have E max equals omega divided by k B max. But since angular frequency over angular wave number, omega over k, is c, we have that the E field is equal to the speed, c, times the B field. How beautiful is that? Or you could say that the speed of the wave is equal to the electric field amplitude over the magnetic field amplitude. Wow. These mathematics are so beautiful that we're going to have to stop here to let you ponder this before we go on to the rest of the material in this chapter. But just appreciate how beautiful this derivation is done by Maxwell.